Welcome back, folks. JLand Bio here. We're going to continue our work through Chemistry 2. Start talking a little bit about pre-atomic theory. That is the ideas behind which chemistry really was created. And what's really interesting is that most of what we know about chemistry was really only discovered in the last 150 years or so. So chemistry is a relatively new science if you really think about it. We'll talk a little bit about the atom, subatomic particles, and how to determine the number of protons, neutrons, and electrons in an atom. Let's get started. So hopefully by the end of this video you will be able to explain early models of atomic theory and the conservation of mass. You'll be able to determine the number of protons, neutrons, and electrons in an atom, and also be able to analyze the relationship between atomic mass and molar mass. We got quite a few vocabulary terms here to make sure that we take care of. That includes the law of conservation of matter, law of definite proportions, Dalton's atomic theory, proton, neutron, electron, alpha particles, nucleus, atomic number, and atomic mass units. So just to kind of get started, a long time ago in a galaxy far, far away known as Greece, around 400 BC, a man by the name of Democritus postulated that matter is made up of all small particles called atoms. Now, that major idea kind of stuck for nearly 2,000 years until a man by the name of John Dalton did some work in the early 1800s. And his atomic model really was the center for chemistry moving forward. So the real history of chemistry dates back way back into the ancient Greek times. However, a lot of the newer concepts that we are aware of today really weren't discovered until the 1800s, and some stuff even more recent than that. One of the key things to understand about Dalton's atomic theory is the law of conservation of matter. And he had 5 postulates, so this is really just one of them. When a chemical reaction takes place, matter is neither created nor destroyed. So if you take a look at the equation on the right-hand side, you have one carbon atom on the left side and one carbon atom on the right side. 4 hydrogens on the left and 4 hydrogens on the right. You also have 4 oxygens on the left and 4 oxygens on the right. You cannot create or destroy matter. Now, this is mostly true. There are a few exceptions to this, mainly nuclear reactions. In a lot of nuclear reactions, you actually lose a bit of mass, and that mass is converted to energy. You probably remember the very famous formula, E equals mc squared, and that applies in that concept. So, conservation of matter, matter is neither created nor destroyed, and that is mostly true with the exception of nuclear reactions. Law of definite proportions simply states that multiple samples of any pure chemical compound would make up the same percent mass. Let's use an example of water. Water in lakes, water in a stream, water in the ocean all has the same percent mass of hydrogen and oxygen. It does not change. So all compounds have the same percent mass. To solve for percent mass, we simply take the mass of the element and divide by the mass of the compound. As a result, you'll get the percent mass of the individual element. Let's do a quick sample problem just to make sure we're all in good shape. Here it just simply says to use the data to calculate the percent hydrogen and oxygen in this example. So we have 100 grams of hydrogen, 793.6 grams of oxygen, and that forms 893.6 grams of water. So first off, we can take a look just by the addition process that yes, this does follow the law of conservation of mass, right? That sum is equal to the individual parts. To solve for the percent hydrogen, we're just simply going to take the mass of hydrogen or divide by the total mass of the water. Since it's a percentage, we're going to multiply that by 100. And what we get, using significant figures, 11.19% hydrogen. Now you can go through and do the calculation for oxygen, or if you can just simply recognize that oxygen is the only other element in the compound, you can subtract 11.19 from 100 to get that. Okay? Percent mass calculation is very easy to calculate. Key thing there also to make sure that your numbers add up to 100. So Dalton's atomic theory is pretty straightforward. He basically stated that all matter is made up of small atoms. Atoms cannot be created nor destroyed. Atoms of an element are alike, and atoms of different elements are going to be different than one another in some way, shape, or form. Chemical reactions involve the union or separation of individual atoms, and what's interesting is that most of this still reigns true today, even though it was postulated in the early 1800s. Also keep in mind that John Dalton did not have the technology that we have today to be able to see chemical reactions take place on a microscopic level and to understand the concepts of elements on a deeper level. Mendeleev did not create his periodic table until the mid to late 1800s, so a lot of Dalton's atomic theory was actually before Mendeleev did his work with the periodic table. Really fascinating study in science. To learn a little bit more about the atomic structure, we have to look a little bit further into the future, into 1897, where a man by the name of J.J. Thomson discovered the electron through an experiment using a cathode ray tube. The attraction to the positively charged plate indicated that there was a negative subatomic particle that is present. Now, electrons are very, very small. He actually calculated that this was only 1,836th the mass of a hydrogen atom. Keep in mind that a hydrogen atom typically only contains one proton. This means that the electron has a very, very small mass, especially in relation to what would be inside the hydrogen atom. Now, a couple years later, in 1907, J.J. Thomson and Goldstein discovered the proton. What they did discover was that the proton had a positive charge and was much heavier than the electron. Now, at this time, there really wasn't necessarily a model for the atom. All they really knew is that there was some negatively charged particles and that there's positively charged particles. And so the example that they gave was what's known as the plum pudding model. The plum pudding model is basically the notion that negatively charged electrons, or what they were known back in the time as corpuscles, were distributed in a uniform sea of positive charge. Basically, it's just imagine a circle with a giant positive charge that's in it and little tiny specks of negative charge that are in there. It was called the plum pudding model because the model actually represented plum pudding. The little small electron corpuscles represent the plums, and the sea of positive charge represents the pudding. Now, much later, in 1937, James Chadwick discovered the neutron, which actually had no charge, but had the same mass as a proton. Now, also notice that the proton is much heavier than that of the electron as well. So as we continue to discover more and more subatomic particles, we get a more clear picture of what is inside the atom, as well as potentially what the interior part of the atom looks like. Now, one of the biggest discoveries, and what I'm certainly going to want you to remember, happened in 1909 by a New Zealand physicist named Ernest Rutherford. He actually discovered the nucleus, but really wasn't aware that he discovered it at the time. In order to better understand the model of an atom, he used alpha particles, which are emitted from radioactive material. Alpha particles are basically helium atoms, or helium nuclei, and these were ejected at high speeds towards gold foil. Now, because the plum pudding model was the standard model at the time, Rutherford expected the particles to cruise simply through the foil and off to the other side. But what he actually found was that some of the particles were deflected. There were quite a few deflections of these particles. That indicated a couple things. First off, that the plum pudding model really isn't the best model for that of the atom. In fact, this actually indicates that there's a dense, positively charged area in the center of the atom that caused the particles to deflect either just slightly or to cause them to deflect greatly. This also let Rutherford know that because most of the particles actually did go straight through the gold foil, that the atom is mostly empty space, again, as most of the particles traveled through. While not realizing it, he actually, in a way, discovered the nucleus of the atom, that dense, positively charged area in the center of the atom. So what we know for now, for the time being, is that the atom has a nucleus that contains protons, which are positively charged, and neutrons, which are negatively charged. And the electrons orbit around the nucleus. They are attracted to the protons. A couple of really important numbers that you need to make sure that you know, the first being the atomic number, which is the number on the periodic table. This just simply refers to the number of protons. So if I look at carbon, carbon is number 6 on the periodic table, and that indicates that it has 6 protons in its nucleus. The mass number is the number of protons plus neutrons. Okay? Now that number is typically double or more that of the atomic number. So you can do a little bit of math to figure out the number of neutrons very easily. The mass number is 12, the atomic number is 6, and there are 6 protons and 6 neutrons in this carbon atom. Now, the reason we don't include electrons in the mass number is because electrons are very light. They don't count towards the mass number. Remember, they're almost 1/2000th the size of a proton. So the amount of electrons is fairly insignificant in terms of the total mass of the atom. The electron number are given by the charge of the atom. So if there is no charge, you don't see a charge, then assume that the atom is neutral. In order to be neutral, the number of positive charges have to equal the number of negative charges. So, for example, in the sodium atom, if there were no charge, you would have 11 protons and 11 electrons. Because there is a charge here, that changes the number of electrons. A negative charge would indicate that there is one extra electron. Minus 2, 2 extra electrons, and so on. A positive charge indicates that there is one less electron. So in this instance here, we have an atomic number of 11, which indicates 11 protons. The positive charge would indicate that there are 10 electrons. Do not, under any circumstances, change the number of protons, because if you do change the number of protons, you end up changing the chemical. Remember that protons are what determine what element it is on the periodic table. Again, I know that this is something that you had in Chem 1, but it is important that we practice to ensure that we are in good shape. So what it's asking for is to write out the isotope that contains 11 protons, 10 electrons, and 12 neutrons. Well, let's take a look at the data we have here. We have 11 protons. So if we look at the periodic table, 11 protons is sodium, okay, Na. We know that we have 11 protons. Remember, that number goes down here on the bottom. We also have 12 neutrons. To get the mass number, we need to take 11 plus 12. The result of that is 23. And also notice we have 10 electrons. That indicates that we have one more positive charge than negative, so we put a plus sign in the top right-hand corner. That is how you would write that symbol. In some instances, people also write it out as a word. So for example, this would also be the same as sodium 23. Okay. Many times the charge is not written in this instance, however, that's why we typically write it in that format. Okay? So you should be able to very easily be able to go back and forth between all three of these. The number of protons, electrons, and neutrons, the nuclear symbol, which is what that's called, and writing it out in words. Let's look at the next one. We have 79 Br with a minus charge. So let's go ahead and figure this out. So we know we have bromine. Bromine is number 35 on the periodic table, so the number of protons is 35. Neutrons, well, we have our mass number, right? Our mass number is 79. We know the number of protons. We just need to be able to solve for the number of neutrons. Simple enough. We subtract, we get 44 neutrons. Electrons, notice that there is a negative charge here. That means that there is one more electron than proton. So we have 36. Simple enough. Okay. So if you're really taking away some key points for today, make sure you understand Dalton's atomic theory, a little bit about how some of the subatomic particles are discovered. There's certainly Rutherford's experiment, and to be able to calculate the number of protons, neutrons, and electrons in an atom. Have a great day, guys. We will talk to you later and see you in the next video. JLand Bio, signing out.